All right, I want to talk a little bit about how rate-free response questions work. Obviously, calculus is the study of change, and as a result, rates of change are going to be very, very important on the AP exam. Remember that a rate, when I talk about a rate or a rate of change, I'm really talking about a derivative. Okay, when I'm talking about a derivative, many times I'm really talking about a slope. So, if you see references to slope, or you see a reference to instantaneous rate, or if you see a reference really just to the term rate, you should be thinking about derivatives, okay? One of the pretty typical types of problems they'll give you on the AP exam are problems where they give you a function that is a rate function. And you have to kind of remember that if it's a rate function, it's really a derivative. It's the rate of change of some other function, okay? And so here's a kind of typical example of this. And this really goes back to the first week of the school year as far as the concept goes. The specifics of working with it, of course, are later in the year. But so let's say that it's snowing, okay? And let's say that there are 3 inches of snow on the ground when they start recording this problem. Okay, so when t is equal to 0, we've got 3 inches of snow on the ground. Maybe we could say that s of 0 is equal to 3, something like that, okay? Most of these problems will have an initial value, and it's really important. I always kind of box it in or something to remind myself, because it's easy at the end of the problem to do all the calculus and forget that you had that other information at the start. Okay, so let's say that we have this snowfall rate function. It's not how much snow is on the ground, it's how fast the snow is falling, okay? So let's say there are already 3 inches of snow on the ground. We're in the middle of this blizzard, okay? And the snow is snowing maybe at 5 inches per hour, and it's snowing really quickly, and the snowstorm kind of cuts down over time, okay? And maybe we've got hours on this axis. Maybe by hour, let's say by hour 4, the snow is down to that. But when we start out, it's snowing 5 inches per hour, and by the 4th hour, maybe it's snowing at like 2 inches per hour, something kind of like that, okay? Remember that a rate is really a derivative, okay? So, they could call this r of t, but it's really the rate of change of the snow over time, which means you can also think of this as being s prime of t. And if I ask you, for example, how much snow is on the ground after the 4th hour, you should be thinking, oh, I have the rate of change of the snow. I have the derivative of the snow function, okay? If I want to know how much snow there is, and I have the derivative, you go backwards. You take the integral, and that would allow you to find some information about s, okay? But the other thing here is, if you remember, if you think about the units here, if you found the area under this curve, I have hours, time in hours on this axis, and I have snowfall in inches per hour, okay? If you had a square, and one dimension was hours, and one was inches per hour, and you multiplied those two things together, if you took inches per hour and multiplied by hours, the hours would cancel, you'd be left with inches, okay? The area under that curve for any time interval tells you how many inches of snow fell over that interval, okay? Now, there's a reason I'm doing this right after motion problems, because if you remember, a lot of the motion problems, they were starting you off with the velocity function, okay? And you found, the velocity is the derivative of the position function. And so what you were doing was you were finding the integral of velocity over a time period, and that told you your displacement. That told you how much your position changed over a time interval. Okay, this interval, if we start out with a rate, if we start out with a derivative, tells us how much change happened because of that rate on that time interval from 0 to 4, okay? So, let's say you want to know how much snow fell over this time period. You would take the integral of either s prime of t, or if you remember the original function, I called it r of t, it was the rate of the snow, okay? You would take the integral of the rate between whatever my starting time was, and that's where this started out, and 4. And let's say that equaled 8, okay? That means 8 inches of snow fell, okay? This is sometimes referred to as an accumulating function. If you integrate a derivative, if you integrate a rate, it tells you the change that occurred over a time interval. So 8 inches of snow fell. Now, is that how much snow is on the ground at the end of 4 hours? No, okay? They might be asking me to find s of 4, okay? Yes, 8 inches of snow fell over that time period, but we only had 3 inches of snow on the ground. So in these problems, you're always integrating a rate to tell how much change happened, just like you integrated a rate, a velocity, to find out how far you traveled when we were doing the motion problems. But again, when you found a displacement, that didn't tell you what your final position was. You had to add that to your beginning position, okay? We started out with 3 inches of snow. We had 8 inches of snow added. That means at the end of 4 hours, there are 11 inches of snow on the ground, okay? That's the big idea coming into this section. Now, one additional thing that you're gonna run into in these rate problems. So you're integrating a rate to find out how much change happens over a time period. One other thing they're going to do a lot, I think you're going to see this in the first free response, they're a lot of times going to give you the rate that something comes in, and they're going to give you the rate that something goes out. Let's say that I had an R of t, and that was the rate at which snow falls. Okay, and let's say I had an M of t, and that's the rate at which snow melts. Okay, so for example, maybe it's snowing at, sometimes if you make up numbers, you can figure out what to do here. So let's say you wanted to find out how much total snow there was on the ground over a certain time period. You could actually, so this is the rate at which snow is falling. Maybe snow is falling at 3 inches per hour, something like that, okay? Maybe snow is melting at a 1/2 inch per hour, okay? If I want to figure out how much total change there was, either I can figure out how much snow fell, and then separately I can find out by integrating how much snow melted, and then subtract those two. Or you could just find the overall rate. How much snow comes in an hour, 3 inches every hour, how much snow is melting every hour, 0.5. If you subtract those two things, you're told that we're basically getting 2.5 inches per hour of snow. In other words, if you want the overall rate of change, you can take the rate that the snow is coming in, and you can subtract the rate that it is leaving at, okay? And for example, if I wanted to find out how much snow accumulated from time 0 to time 5, I could take the integral of that rate, okay? That would tell me how much came down over that time period, and this would tell me how much snow melted over that time period. Subtracting the two would end up telling me the total amount of snow that accumulated over that time period, which you would want to add to whatever the initial value was, okay? So that's the background that you need. Again, we've got the calculus here, but we just have to kind of twist it to fit into the problems, and I think those are usually some of the little things that maybe haven't come up in previous problems. Hope that helps as we start to get into some of these questions.